In this video, we're looking at a kinematics problem where I have two distinct phases happening. So I have a car that starts with a known initial velocity of 23.2 meters per second, and then the driver puts the brakes on, and that induces an acceleration of 5.4 meters per second squared opposite to the direction of the velocity. In other words, it's slowing down. It does this for 2 seconds, and then the driver releases the brake, and the car just coasts at a constant velocity for another 3 seconds. So we have a constant negative acceleration phase followed by a constant velocity phase. In part A, we're looking for the velocity of the car after the braking phase. So I have an initial velocity, I have a known acceleration, and I have to be careful about the signs here. If I'm using positive for the direction of the velocity, then the acceleration is surely negative. And then I have a time for this process. I was told this happens for 2 seconds. And then I'm looking for the final velocity at the end of that process. So this is just constant acceleration, kinematics, and I write down my velocity equation. V equals V naught plus AT, and that gives me 23.2 meters per second minus, because my acceleration was negative, 5.4 meters per second squared times the time this occurred for, which was 2 seconds. And I get a final velocity of positive 12.4 meters per second. So that means 12.4 meters per second to the right. So that's going to be the constant velocity for the second part of the process. In part B, I'm asked for the total displacement from t equals 0 to t equals 5. In other words, for the entire thing put together, 2 seconds of braking, 3 seconds of coasting. So if I start by writing down the position as a function of time for constant acceleration kinematics, just a quick technical point here. I can subtract x naught from both sides. That's the initial position. And x minus x naught, the final minus initial position, I could also call that the displacement. So what I'm going to do is write down the displacement for the first phase, and I'll call that delta x1. And that's going to be v naught t plus 1/2 at squared. So that's 23.2 times 2 minus, because the acceleration is negative, a 1/2, 5.4 times 2 squared. And this gives me 35.6 meters of displacement during the braking phase. And then I look at delta x2, that's the displacement during the coasting phase. And in that phase, a is equal to 0, so the acceleration term vanishes. And I simply get v naught times t, in other words, just a simple distance equals rate times time kind of thing. And the speed during the coasting phase, we already solved for that. That's 12.4 meters per second. And it goes on for 3 seconds. This gives me another 37.2 meters of displacement. And to wrap things up, I want to find the total displacement. That's 35.6 plus 37.2. And this gives me a total of 72.8 meters. And we're done. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.